Okay, for this video, we're going to be looking at J.J. Thomson and his contribution to our understanding of the atom. Now, J.J. Thomson is famous for his cathode ray tube experiment, which is this apparatus right here. And basically what's happening is you take a vacuum tube, vacuum meaning there's nothing inside of it, no air, no other molecules at all, and you attach it to some wires and run electricity through it. When you do that, you end up with this beam that you can see right there, right? And basically, once he created this beam, and he didn't really know what it was, there was nothing in the tube until he ran electricity, and all of a sudden there was a beam of particles. He applied a magnetic field to the beam and was able to notice this, that the magnetic beam actually bent up towards the positive side of the magnet, which told him that that it was a negatively charged beam. Okay, we know that because in magnets, opposites attract. So a negative is attracted to a positive, and we can see that's being repelled also by this negative down here. So he did a cool experiment to determine the mass of those particles in the beam and found that those negative charges that were in that beam were 1,000 times lighter than the mass of the atom. So John Dalton had said, hey, the atom is the smallest thing. And later, J.J. Thomson came in and said, hey, actually, there's these negatively charged particles that are very small. They're much smaller than a typical atom. So then he did some more experiments. In this experiment here, it's similar to the cathode ray tube, except all he's doing is he's taking some hydrogen. He's shooting it through his electron gun here, but in this case he's just shooting hydrogens. And those hydrogen atoms are run past a pair of magnets, a magnetic field. Now you'll notice it doesn't do anything, which is really interesting because J.J. Thomson just saw, hey, wait a second, there are some particles in atoms that have a negative charge. So how come these hydrogen atoms aren't affected by the magnets? And he said, well, wait a second, if the negative charge is there, but they're not being affected by magnets, there must also be a positive charge in the magnets that's canceling out the negative because these hydrogens aren't interacting with magnets. So he came up with what's known as the plum pudding model of the atom, where he said, hey, atoms have, instead of just a ball, like Dalton proposed, he said, hey, they're actually a positively charged ball. And within this positively charged atom, there are little negative particles with a negative charge. So his big contribution, his kind of key idea here, is that atoms have, or there are things smaller than atoms, excuse me. In this case, he said the electron. So he said the electron is a small negatively charged particle within the atom. So already we're seeing the introduction of subatomic particles, things smaller than atoms. And because he noticed that the atom wasn't charged, right? Hydrogen didn't do anything next to magnets. He said, well, there must also be this positive charge within an atom, that the atoms are full of positives and negative charges. And the electrons, those little negative particles within the atom, are balancing out the positive charge of the atom.